Hello everyone, I am Mr. Ashish Chaudhary, Assistant Professor of Mechanical Engineering Department of Vidyaprasarag Mandals, Moharji Parshuram College of Engineering, Bhubaneswar. So in previous lecture, we have started about the chapter Vapor Compression Refrigeration System from Refrigeration and Air Conditioning subject. Okay. In that we have already discussed about the vapor compression refrigeration system. So here there are the four main parts. We will start from the compressor. So for the compressor we will supply the work done in the form of mechanical work. So here the low pressure and low temperature refrigerant is inlet to the compressor. After supplying the work done, we will increase the pressure of this refrigerant and it will be available in gas form. So outlet of the compressor we have high pressure and high temperature gas refrigerant. That refrigerant we are supplied to the condenser. Here heat will be removed from the refrigerant. Due to that, at the constant pressure and constant temperature, the gas refrigerant change its phase and convert it into liquid refrigerant. So outlet of the condenser we have liquid refrigerant with high pressure and high temperature. Then we have the receiver. Receiver just a storage tank. Okay. After that we have a main part is expansion device. So this is a just a wall. During this expansion, the expansion device, the throttling process will be carried out. In that, the high pressure liquid refrigerant will be converted into low pressure liquid refrigerant. If pressure will be reduced, obviously temperature of that refrigerant will be reduced. So at outlet of the expansion device, we have low pressure and low temperature liquid refrigerant. That low pressure and liquid refrigerant we are supplying to the next as the evaporator. Here heat will be absorbed by the refrigerant which is available at a low pressure and low temperature in the form of latent heat of evaporation. That after the absorbing that amount of latent heat, that liquid refrigerant will convert it into the gas refrigerant. But this process is available at low pressure and low temperature, constant low pressure and constant low temperature. Now at the outlet of the evaporator we have low pressure, low temperature gas refrigerant we have available. That we have supplied to the compressor again. Again the compression process will be carried out. Then it is supplied to the condenser. Here condensation will be carried out. Then it is supplied to the expansion wall. Here throttling process will be carried out, and again it is supplied to the evaporator. Here heat will be absorbed. Okay. So this is about the theoretical vapor compression refrigeration system. Okay. In that we have studied the first type of vapor compression refrigeration system as the cycle with a dry saturated vapor after compression. So here is the graphical representation of a theoretical VCR, means vapor compression refrigeration cycle with a dry saturated vapor after compression. Okay. So first graph as a temperature versus entropy graph, and second is pressure versus enthalpy graph. So in that we have started from the compression process, just we have discussed earlier. So we have 1 to 2 process as compression, 2 to 3 as condensation, 3 to 4 is expansion, and 4 to 1 again evaporation. Okay. So that graphs we have plotted here. Okay. So here, so our system is with the dry saturated vapor after compression. That means the point number 2 is available at the saturated gas line. So if you see here, this is the saturation curve lines. So this is at the top point we have a critical point. So here also a critical point. Okay. So at left hand side of the critical point as the saturated liquid line, and right hand side of the critical point as the saturated gas line. So same again here, left side of the critical point there is a saturated liquid line, and here the at right side saturated gas line. Okay, so as stated, we have the dry saturated vapor after compression. So dry saturated vapor is available on this saturation gas line. So we have plotted here the point number 2 at outlet compressor pressure and outlet compressor temperature. Okay. So here is the point number 2. But the process 1 to 2 is a compression process, and for our simplicity, or we can say here the theoretical VCR system. So for theoretical system, 1 to 2 process compression process is considered as isentropic compression process. Okay, so for that constant entropy process, so this is the line available for the pH diagram. But same in the TS diagram, the 1 to 2 there is a vertical straight line. That means S1 is equal to S2. Entropy available at point number 1 is equal to entropy available at point number 2. Okay, so this is the presentation of the first process 1 to 2 compression. Now second process is a condensation process. So condensation process is available at a constant pressure and constant temperature. Okay, so this is the 2 to 3 process. So at constant pressure and constant temperature, so these are the representation of this process. But what will happen in the condensation process? In the condensation process, latent heat of condensation will be rejected by the refrigerant. So that is QR. So 2 to 3 process is condensation. So here latent heat of condensation will be rejected by the refrigerant, and the gas formed refrigerant will be converted into liquid form. So that's why the process will be start from the saturated gas line and end at the saturated liquid line. Same again here. Okay, so this is 2 to 3 is the condensation process. Now 3 to 4 we have the expansion process. 3 to 4 is expansion, that means throttling process, and we have already studied in thermodynamics. Throttling process is always considered as constant enthalpy process, and again we have said that this is a theoretical system, so that's why enthalpy of this process is the constant. So if you see in the pressure enthalpy graph, the 3 to 4 process is a throttling process, expansion process, which is available at constant enthalpy. So H3 is equal to H4. So that's why we have the vertical straight line. Okay. Now, but 4 number point is available at evaporator pressure. So that's why the expansion will be carried up to the evaporator pressure. So this is the point number 4. Same again here, but on TS diagram, this straight line in pH graph is not straight line here, it is a curve. Okay, so this is the constant enthalpy line into the TS diagram. So this is about the TS. But what will happen? 4 number point is available at the evaporator temperature. Okay, so this is one, and we know that evaporator temperature, this is constant one. Now the process 4 to 1. The process 4 to 1 is represented as evaporator process or the evaporation process here. Okay, so in that what will happen? The refrigerant absorbed its latent heat of evaporation from the surrounding medium, and change of phase will be takes place. So that's why liquid refrigerant will be converted into gas refrigerant. But in actual happen, what will happen here? The expansion wall, when the high pressure refrigerant will be throttled through the expansion wall, some during the conversion into low pressure, some of the liquid refrigerant will be converted into gas refrigerant. Okay, so that's why if you see here, the point number 4 is not available on the saturated liquid line and the both gram. So now about the evaporation process 4 to 1. So here latent heat of evaporation will be absorbed by the refrigerant, and the phase change will be take place. But if you see here, obviously 4 number point is available at mixture in the form of liquid vapor mixture. So that's why this point is available not on the saturation curves, it is available inside of the dome. So this region is liquid plus vapor mixture. So 4 number point is available with liquid plus vapor mixture, and 4 to 1, the whatever the liquid is available, that will be converted into the gas phase after absorbing latent heat of evaporation. So this is the process 4 to 1. Now we have here the compressor work. Compressor work is calculated as mass flow rate of refrigerant multiply with H2 minus H1. Okay. Now here the refrigerating effect so compressor work done, the process is 1 to 2, and refrigerating effect this is available at the evaporator, that means process is 4 to 1. So here again it is multiply of mass flow rate of refrigerant multiply with H1 minus H2. Okay. Now here COP, coefficient of performance of this refrigerator, is, we know that refrigerating effect divided by compressor work. So this is equal to is m dot r H1 minus H2 divided by m dot r H1 minus here H4. So this is the refrigerating process 1 to 4. So H1 minus H4, so H1 minus H4, and compressor is 1 to 2, so higher minus lower. So COP of refrigerator as H1 minus H4 divided by H2 minus H1. Okay, so this is about the COP. Okay. Now the next process as the theoretical vapor compression refrigeration cycle with wet vapor after compression. Okay. So what we have, the second type of the VCR system as we are getting wet vapor after compression. Okay. So this is the graphical representation of theoretical VCR cycle with wet vapor after compression. So this is the TS diagram, temperature versus enthalpy diagram, and pressure versus enthalpy diagram. So here what we have said, wet vapor after compression, that means after compression process we are getting the refrigerant in the form of liquid and vapor mixture. So that's why if you see here, if you see in the previous type, just like here, the point number 2 is now available inside of the dome. So this is the region of liquid plus vapor mixture. So that's why, and we know that the first one, our cycle is theoretical one. So process 1 to 2 compression process is considered isentropic process. So that if point number 2 is available inside of the dome, obviously 1 number point is available as inside of the dome, or we can say it is a liquid plus vapor mixture. Okay. So 1 to 2 process as a compression process. Now 2 to 3 is similar, again the condensation process. Here latent heat of condensation will be rejected by the refrigerant at constant pressure and temperature, and the whatever gas is available, that will be converted in the liquid form. So that's why point number 3 is available on saturated liquid line. Same again here, at the constant temperature the process becomes 2 to 3, and 3 number point is available on saturated liquid line. Now similar with previous cycle, 3 to 4 is throttling process, and you know that throttling process, the throttling process here the enthalpy is constant, so again H3 is equal to H4. Okay, so here in pH diagram this is a vertical straight line, but in TS diagram it is a inclined curve. Okay, now 4 to 1 is a evaporation process, and in the evaporation process already we have stated that point number 4 is also a liquid vapor mixture, so that's why it is available inside of the dome. And now the process 4 to 1 evaporation process, in that latent heat of evaporation will be absorbed by the refrigerant. Okay, so here the QR and here is the QE. Okay, and when the refrigerant absorbs its latent heat of evaporation, then it will be phase change will be take place. So some part of the liquid refrigerant will be converted into gas form. So that's why we have the point number 1 here. 1 to 2 is isentropic process. So for the isentropic process we have already stated the entropy is constant, S1 is equal to S2. Now what is the change? In the change, the previous and second type, as the point number 1, point number 2, we have the dryness fraction. Okay, so this is as the X1 and the X2. So dryness fraction indicates what is the percentage of the gas refrigerant is available into the mixture. So dryness fraction. By using the dryness fraction we can find out the enthalpy of a corresponding point. Now in actual practice, theoretical VCR cycle with wet vapor after compressor is not in use, because the 1 number point, if we are supplying the liquid refrigerant to the compressor, then there is a possibility of corrosion of the compressor parts. So that's why, so this cycle we are not using. Instead of using this one or the first one, what will happen in first and second type, the point number 1 is a have some dryness fraction. That means there is a liquid form of refrigerant is available, and due to that this we are not supplying this type of refrigerant to the compressor to avoid the damage of the compressor parts or the corrosion of the compressor parts. Okay. So this is about the cycle. Now what will happen here? Okay. So what will happen here? Again COP. If you see here, theoretical vapor compression cycle with wet vapor after compression. Same formula we can use, as compressor work as mass flow of refrigerant multiplied with H2 minus H1. Refrigerating effect is equal to mass flow of refrigerant multiplied with H1 minus H4. And COP is again refrigerating effect divided by work done is equal to mass flow of refrigerant multiplied with H1 minus H4 divided by mass flow rate of refrigerant multiplied with H2 minus H1. So if you cancel this one, we will get the COP as H1 minus H4 divided by H2 minus H1. Same formula we can apply for second type also. Now here the third type of vapor compression refrigeration cycle as theoretical vapor compression refrigeration cycle with superheated vapor after compression. We have already studied the process number 1 to 2 as a compression process. So that's why what we have given the superheated vapor after compression. That means whatever the outlet of the compressor is available, it is available into the superheated region. So where is superheated region? If you see here, this is a critical point, and right hand side curve of the critical point we have stated as a saturated gas line. Okay, then the right side region of the saturated vapor line or gas line is considered as a superheated vapor region. Okay, so that means the point number 2 is available into this region. Okay, so this is again. But if you see here, the again we consider it is a theoretical VCR cycle. That means the compression process is available as a isentropic compression process. So we will consider as S1 is equal to S2. Okay. So that's why into the TS diagram we have a vertical straight line. Now in the pH diagram it is an inclined line, because inclined line is indication, or this is the line is a constant entropy line into the pH diagram. So this is about the compression process 1 to 2. If you consider when the point number 2 is considered as a superheated region, the point number 1 is available inside of the dome or outside of the dome, depend upon the temperature at a point number 2. So but for this cycle we will consider as point number 1 is available at a saturated vapor line. So that means we will consider that at the inlet of the compressor we have a dry vapors we are supplying to the compressor. Okay, sometimes this point number 4 will be inside of the dome. So that means at inlet of the compressor, sometimes for this type also there is a wet mixture is available, but for this we will assume that the point number 1 is dry saturated. Okay. Now 1 to 2 is a compression process. Now 2 to 3 is as it is constant pressure heat rejection, that means condensation process will be taking place. So in pH diagram this is available at constant pressure, that means the point number 2 from superheated region will be moved toward the saturated liquid line. Okay, so point number 3 is available as stated previous types also on the saturated liquid line. What about the point number 2 dash? So 2 dash point is available as when the process will be carried out, the temperature will be reduced of the refrigerant with some extent, and we are getting the temperature available on a saturated gas line or the vapor line. So that's why if you see here at a constant pressure into TS diagram, this is the inclined line indicate the constant pressure line. Okay, but inside of the dome the horizontal line is considered as again constant pressure line. So this is constant pressure. So this is about the constant pressure line into the TS diagram. So at a constant pressure the temperature of the point number 2 will be reduced, and this is ending at the condensation process, and the point number 3 is available on saturated liquid line. Okay, so this is about the condensation process. Okay, now here after that if you see here the throttling process is as it is available at the constant enthalpy process. H3 is equal to H4, that means in pH diagram it is a vertical straight line, and on TS diagram it is an inclined curve. Okay. Now the 4 to 1 is the evaporation process. The refrigerating effect will be done, the heat will be absorbed by the refrigerant, and the point number 4 will be transferred at point number 1. So process will be carried out. Now here then how to find out the H2? So H2 is equal to, so before find out the H2, how to find out the S2? S2 is equal to entropy at point number 2 is equal to S2 dash plus Cp log to the base E T2 dash divided by T2. By using this one we will find out the entropy at point number 2. After finding this we will also find the entropy at point number 1. Okay, but if you see here the 1 to 2 is the constant entropy curve, that means we can find out by using S1 is equal to S2 also. Okay. Now and what about the enthalpy? Enthalpy at point number 2 is equal to H2 dash plus Cp T2 dash minus T2. So by using this formula we can find out the enthalpy at point number 2. Okay. Now next cycle as the theoretical vapor compression refrigeration cycle with superheated vapor before compression. Okay. Superheated vapor before compression. Now about the theoretical VCR cycle with a superheated vapor before compression. Just like previous cycle, as after compression we are getting superheated. After compression we are getting the superheated vapor. Similar to that, here the fourth type as the theoretical VCR cycle with superheated vapor before compression. That means point number 1 is also available at the superheated region. If point number 1 is available in the superheated region, obviously point number 2 after compression is also available as a superheated region. Okay, so here the 1 is available in superheated region. So 1 to 2 is isentropic. So here S1 is equal to S2. Okay, so here 1 to 2 is isentropic compression process, inclined line. Then 2 to 3 is condensation process. In that, during the condensation process, when at a constant pressure heat will be rejected by the refrigerant, we are getting the point as the temperature corresponding to the saturated gas line. So that point is indicated here as a 2 dash. So if you see in the TS diagram, at a constant pressure the heat will be rejected by the refrigerant, and during the phase change what will happen, first temperature of this gas refrigerant will be reduced. That means degree of superheating, if you consider this is as a degree of superheating, 2 to 2 dash, 1 dash to 1, 2 dash to 2 and 1 dash to 1, it is a degree of superheating. That means first temperature will be reduced, so obviously here temperature will be reduced, and after that when we are getting the temperature corresponding to the saturated point available on the vapor line, and then condensation will be taking place. So here 2 dash to 3 is actual condensation process. So again 2 dash to 3. So in condensation process we have already stated the phase change will be available, and the phase change obviously it is starting from the gas to the liquid. So 2 dash to 3. So 2 dash is available at saturated vapor line and 3 is available on saturated liquid line. So latent of condensation. But here actually condensation process we are considering from the point number 2 to 3. Total heat will be rejected. Now here 3 to 4 as it is the throttling process, and this is considered as a constant enthalpy process, though here H3 is equal to H4, constant enthalpy process. Now the 4 to 1 dash, here the now evaporation process will be taking place, started, and latent heat of evaporation will be absorbed by the refrigerant, and the whatever mixture of the refrigerant is available, that will be directly converted into gas form. So here we are now getting the same refrigerant at the low pressure and low temperature at the saturated vapor line. Now here the same refrigerant in the gas form, again we will increase the temperature and it is supplied to the compressor. So this is 1 dash to 1. Okay, so this is called as a degree of superheating. So we are superheating the gas refrigerant at a low pressure and low temperature. So this is the superheating of the refrigerant before the compression. And formula is available as the same. The COP is as H1 minus H4 divided by H2 minus H1, because H1 to H2, this is H1 to H4, this latent heat difference is considered as a refrigerant effect, and H2 minus H1 is considered as a compression process. And how to find out the degree of superheating? By using degree of superheating we can find out the entropy as S2 is equal to S2 dash plus Cp log E in bracket T2 dash divided by T2. So S1 is equal to S2 as it is, and H2, if you find out the enthalpy at the point number 2, it is equal to H2 is equal to H2 dash plus Cp of the refrigerant multiply with the degree of superheating. So T2 dash minus T2. So same formula we can apply it for the to find out the enthalpy at point number 1. So H1 is equal to H1 dash plus Cp in bracket T1 minus T1 dash. So here, not here the T2 dash, here is the T2 dash. H2 is equal to H2 dash plus Cp T2 minus T2 dash. So this is about the enthalpy, to find out the enthalpy at point number 1 and point number 2. Okay. Now the last type is we have theoretical VCR cycle with undercooling or subcooling of the refrigerant. Okay, so now here, now last type is theoretical VCR cycle with undercooling or subcooling of refrigerant. Okay, so for that we will consider as a compressor condition as at the inlet of compressor we have a dry saturated vapor, and outlet of compressor we have the superheated vapor. So that's why the point number 1 is available on dry saturated vapor line and point number 2 is available in superheated region. So same in pH diagram also. But in the condensation process, now in the condensation process, so condensation process takes place at the constant pressure and constant temperature. But in first time, when superheating condition is considered, so during superheating condition, first at a constant pressure, temperature of that the vapor will be reduced. So this is reduced from T2 to T2 dash, and from T2 dash the condensation, actual condensation of the refrigerant will be takes place, and T2 dash to 3 is phase change will be taking place from gas to the liquid. So point number 3 is available as a dry saturated the liquid point. Okay, same again here, but again what we have given the process as undercooling or subcooling. So subcooling will be taking place, that means liquid refrigerant will be again cooled. It is called as the undercooling or subcooling. So that means the point number 3 again is available at the left hand side of the saturated liquid line. So that's why the temperature of this liquid refrigerant again reduced at the constant pressure. So this is the constant pressure line. So what will happen? If you see here, the temperature reduced from 3 to 3 dash. So 3 dash point, so it is called as the undercooling. So temperature 3 to 3 dash is called the degree of undercooling or subcooling. And again the expansion process will be carried out from 3 dash point to 4. So 3 dash point to 4 at the constant enthalpy. So H3 dash is equal to H4. So here the 1 to 2 is S1 is equal to S2, entropy is constant for the compression process, enthalpy is constant for the expansion process. And now for the evaporation process, 4 to 1 as it is, the point number 4 is available at liquid vapor mixture. Okay, because during the degree of superheating, degree of undercooling, the point number 3 will be shifted into the subcooled liquid region. So left hand side region of this liquid line, saturated liquid line, is considered as the undercooling or subcooled region. Okay, beside that the point number 4 is also available at the liquid vapor mixture. That refrigerant we are supplying to the evaporator, then here latent heat of evaporation will be absorbed by the refrigerant and the total refrigerant will be converted into dry saturated vapor. Okay, now here just like previous types, to find out the enthalpy at H3 is equal to H3 dash is equal to H3 minus Cp in bracket T3 minus T3 dash. So by using this formula we will find out the enthalpy at point number 3 and 3 dash, and we know that H3 is equal to H4 H3 dash is equal to H4. By using this one, we will use to find out the enthalpy at point number 4, and by using that we will find out the COP of refrigerant as H1 minus H4 divided by H2 minus H1. So this is about the COP of system. So by using this one, we will study the vapor compression refrigeration system. Thank you.